Hello students, in this video we are going to talk about eigenfunction expansion. Okay, so let me start with some preliminaries and then we'll see what exactly are you trying to do here. So first of all, see, the thing is in Rn, let's say that let E1 E2 En. Okay, so this be the basis of Rn, right? Basis of Rn. Is it okay? And then if this is the case, then every, let's say, x in Rn, okay, for every x in Rn, so there is a unique choice. There is an unique choice of constants. Okay, what is the constants? Alpha 1, alpha 2, alpha n, for which x equals to summation I equals to 1 to n alpha I ei. Is it okay? I can write it like this. Now you see, let's say that if such a representation is already given, or let's say if we given any eigenvalues, given a basis, and if we want to find out what the ai alphas are, okay, how do you do it? See here, what we are using is this. Now since eis are orthonormal, okay, for all I between 1 and n, what you can do is this. You can actually see what is the action of x on ei. Is it okay? And what is that? That will be nothing but the summation alpha I ei acting at ei. Okay, I equals to 1 to n, and that we can use the linearity property of the dot product, and we can write it like this, right? So this is nothing but summation of alpha I ei acting at maybe I can write this thing as ej, that will be fit better. So basically I want to find alpha j, that is so okay, this is fine, and then ej. Is it okay? Now if we do that, so I equals to 1 to n. Okay, so I'm just taking any j between 1 to n, I'm just writing it like this. Okay, so if I do that, then you see ei ej, essentially what is happening is this. I should write I here. ei ej, you see, for I equals to j it is 1, otherwise it is going to be 0. So that will actually give me the coefficient alpha j. Okay, and this holds for every j between 1 and n, right? Okay, so hence the unique representation given orthonormal basis. Here's the unique representation given an orthonormal basis. Orthonormal basis is x can be written as summation. You see, the coefficients is nothing but x acting at ej, okay, and times I equals to 1 to n. Clear? So that's your unique representation, and that's how you write any element x in terms of its normal orthonormal basis, that is. Yeah. Now you see, we want to generalize this idea. Is it okay? So basically, let's say given an orthogonal set of functions in some interval alpha beta, yes, with respect to some weight, let's say Rx, yes, can we represent an arbitrary function? So the question now is this question. Question is this. Given, okay, an ortho, so here it is orthonormal basis, right? So let's just start with the orthogonal basis. Okay, of course we can make it normal. So let's start with the orthogonal basis now. Okay, so orthogonal basis, and what is it? Phi n. Okay, phi n, and n equals to 0 to infinity. So the orthogonal basis given like this. Okay, orthogonal basis, yes, in the interval alpha beta, is it okay? With respect to the weight, with respect to some weight, okay, with respect to the weight Rx. Is it okay? Now, the thing is this, can we represent another function? Okay, let's say f of x. Nice enough. Of course, you can't expect that you can represent any function like that, but nice enough, let's say. Yes, we don't know what nice enough means right now, but let's just, I mean, it's a nice function, exponential, sine, cosine, that sort of function. Can we do that? That's the question. As an infinite series, okay, involving phi n of x. Is it okay? So essentially, f of x should look like this. You see, summation n equals to 0 to infinity Cn phi n of x. Is it okay? See, if you remember, why are we writing this as infinite series? Because the orthonormal sets which we are getting from the Sturm-Liouville problems, we talked about it, right? So if you have a regular Sturm-Liouville boundary value problem, yes, you are going to get, let's say that for a distinct eigenvalues, right? So you are going to get eigenfunctions, and those eigenfunctions are orthonormal to each other, right? Yes, that we know. Yes, and the thing is, this is like an infinite series, right? So basically, you see, there is a way of actually producing an orthonormal basis. Now the thing is, the question is this: can we use that idea to represent any function? Is it okay? So let's understand this, what happens. Okay, without going into, I mean, proper mathematics, let's just quickly understand that how should we formally proceed. Okay, so how to formally proceed without convergence, without the question of convergence. What does it mean? See, in the earlier case, okay, when we were in Rn, it was like a finite number of points. You see, this series which we are talking about, okay, summation alpha I ei. This is like from I from 1 to n, right? So it's a finite series. In case of finite series, you really don't have to worry about convergence because it's like a finite sum, right? But once we have like infinite kind of cases, then we have to talk about convergences. Yes, we don't know whether this actually converge or not. So what we are going to do is basically, without the equation of convergence, let's just assume that all of these converges, they are nice, everything is fine. And can we find the coefficient Cn? That's just the question. Okay, so what we do is this. See, basically such that fx must look like summation n equals to 0 to infinity Cn phi nx. Can we do that? Yes, let's just understand that. Okay, so what we do is, let's just call this as 1. So we multiply 1 with r of x times phi m of x. Is it okay? We just multiply it and integrate between alpha to beta, and integrate between alpha to beta. Is it okay? Yes. What do we get? You see, if you multiply between integrate between alpha to beta, r of x phi m of x f of x, right, dx. That's what we are going to get. I am multiplying by r of x phi m of x. Clear? So that will be written right, alpha to beta summation n equals to 0 to infinity Cn r of x phi n of x phi m of x dx. Is it okay? See, similar sort of thing what we are doing here. Here we are multiplying it by Rj, Ej, right? That's my basis kind, the orthonormal basis. Now here I am multiplying with my orthonormal basis element phi n, but there is a weight involved, right? R of x. So basically we are incorporating that R of x also here. Right. So once we do that, you see the thing is here there is a problem. If I want to take this integral inside this summation, there is a problem. But the thing is we are just assuming that we can do that. Let's just assume that. Yes. So once you do that, then what happens is this. See, from here what can you write? This is summation n equals to 0 to infinity. Yes. And this integral is from alpha to beta. Clear? R of x phi m of x. Okay. Phi n of x dx. Yes, and that is nothing but alpha to beta, okay, r of x phi m of x f of x dx. Is it okay? Yes. And by the way, what about this? This is nothing but, you see, this is a, let's say this is the orthonormal basis, right? Phi n's are orthonormal. So basically for I n not equals to m, we have basically we have the integral alpha to beta. It is orthonormal with respect to the weight r, right? So basically r phi n, the integral of that is going to be 0 for all n not equals to m. Yes. So the only part which is remaining is m equals to m. So in that case, it is just the r of x norm of phi m square. Yes, between alpha to, okay, 1 second, sorry, it is not r, sorry, I made a small mistake somewhere, right? That cm is, I did not write it. Yeah, I'm really sorry about it. Let me just write it. This cm should be there, no? Cn, cn, let's just write it, cn. Okay, now you see the thing is, this is the only thing which is remaining is cm times norm phi m square. Is it okay? And then this part, what we have is, this is alpha to beta r of x phi m of x phi n of x dx. Is it okay? Yes. So therefore what we have, cm is nothing but alpha to beta r of x phi m of x phi n of x dx by norm of phi m square. Okay, phi m is orthogonal, right? So phi m square is of course not 0. Yes, and if it is orthogonal, so basically that will be 1 in that case. Yeah, if we start with that. Okay, so in that case, cn will be just a to b, alpha to beta r phi m dx. Yeah. Okay, so see, the thing is, therefore, see, if this operation, the first operation, the integral and the sum, okay, if we can, interchange that. So basically, when can we do it? So basically, if the series, what is the series? Summation n equals to 0 to infinity cn phi n of x, okay, if it converges uniformly, in alpha beta, then the above, okay, procedure is justified. I hope it is clear to you. Very simple, very simple. Okay, now the thing is this, see, the coefficient cn which you are going to get, this cm's which you are getting, those coefficients, if let's say all of this is possible, so the series convergence uniformly and everything is fine, then what we are going to do is we are going to call this thing as the Fourier coefficient of the function f of x. Is it okay? Right. So now let's look at a problem and then we'll go from there. Okay. So first start doing a problem. So example 1, let's say. So you see, we know that the set, this set 1 cosine n pi x by L sine n pi x by L, and L positive, n is greater than equal 1. Okay, this is orthogonal. This is orthogonal with respect to what is the weight, Rx equals to 1. Rx equals to 1. Okay. Okay, first of all, how do you show this is orthogonal? Of course, you can take the integral and you can show that it's going to be 0 for n not equals to m, or it is going to be not 0 for n equals to m. Okay, that of course you can do. The other way of doing it is basically, you see, y double prime equals to y. You remember that problem we did, y at the point with the periodic solution, this thing with the periodic data. Yes, and we have seen that these are the eigenvalues, right? Yes. Sorry, these are the eigenfunctions, and we know from that theorem which we did in the earlier class also that those eigenfunctions are going to be orthogonal. So you have this set which is orthogonal. You can do that. Clear? So this is orthogonal in minus L to L. So we did it for minus pi to pi, but for minus L to L, this is what you are going to deal with. Okay. Now, of course, then what happens is minus L to L, that is, okay, cosine square n pi x by L dx. This is nothing but 2L and L. Okay, this is for n equals to 0 and this is for n greater than equal to 1. Yeah, and minus L to L sine square n pi x by L dx. This is L for n greater than equal to 1. What about n equals to 0? It is basically 0, so you don't worry about it. Okay. So in that case, you see, by going by this earlier idea, what happens is this f of x. So given any f, yeah. So see, we define something like this. So the Fourier series of f of x is defined to be f of x. Okay, it will look like this: a naught by 2 plus summation n equals to 1 to infinity an cosine n pi x by L plus bn sine n pi x by L. Is it okay? We can write it like this, where, let me just write it. What is an or an? An is 1 by L. Why 1 by L? Because you remember this part is there, phi m square. What is phi m's here? They are like sines and cosines, right? Okay, so an is basically that cosine part. So basically that 1 by L thing is there. You see, phi n square. Okay, so phi n square cosine square. So it is, let me write it. It is 1 by L fx cosine n pi x by L dx. Okay, n greater than equal 0. Is it okay? Let me just once check if everything is fine. What did I wrote? An is 1 by L. Yes, this is fine. Minus L to L. And let us write Bn. So if you can see, if we do the exact same procedure, Bn, this Bn's will be in respect to, sine. Okay, so in that case it will be again 1 by L sine, and this is minus L to L, and it will be just a multiplication. So let me write it. So it is sine of n pi x by L dx. Okay, Bn. So that is there. Now the thing is this. See, the thing is, what we will do is this. So this is fine. So if you do it like this, you can just write down the Fourier series of f of x. So by the way, this Fourier series in particular is called a trigonometric Fourier series. Is it okay? Now the thing is this. You see, as I told you already, that all of this is valid provided the Fourier series converges. Okay. So how are you going to show that this Fourier series actually converges? Okay. And so for this, this theory to work, what we are going to do is we are going to assume, so the convergence of Fourier series. Let's just write it like this. We are going to talk about the convergence of the Fourier series. Fourier series. Okay, so see, the thing is, first of all, we are going to start with some phi n's. So let phi n n equals to 0, 1, 2 and f of x be are piecewise continuous. Piecewise continuous in alpha beta. I hope you guys all know what piecewise continuous in alpha beta means. It basically means that there are finite number of points, okay, where they may not be continuous, except that everywhere they are going to be continuous. So that's what we call all the piecewise continuous. Okay. Now you see, let, and we'll call define S capital N of x. This we are going to define it as the sum of summation n equals to 0 to capital N, the first n plus 1 term, okay, of Cn phi n of x. Is it okay? Yes, and we donate it by capital Sn of x. Yeah, and now you see, we consider the difference. We consider the difference Sn of x minus f of x. Okay, this difference for large values of n, large values of capital N. Is it okay? Now you see, if given epsilon greater than 0, there exists an integer in epsilon which is positive, okay, such that mod Sn of x minus f of x can be made less than epsilon, okay, then the Fourier series converges uniformly, right? Uniformly, okay, to f of x for all x in alpha beta. Is it okay? So the idea is this. See, essentially what we are saying is this: we were approximating f. Yes, and how are we doing it? We are going to use f of phi x, okay, in such a way that we are basically taking the finite sums, and after that we are actually saying that for large n of n, what happens is this: the difference between Sn and f can be made arbitrarily small, right? And if that holds for all x, that is important, then we say it converges uniformly. Is it okay? And of course, if n depends on, so let me make a small remark here. So you guys already know this, but I still wrote it in case of, since there should not be any confusion here about the definition. So what is the remark? See, n, the capital N, okay, here depends only on epsilon, only on epsilon, and not on x. Clear? And not on x. So if it depends on x also, then we basically say this is a pointwise converter. Okay, right. So now let's look at a definition. Let me just write down the definition, and then I will try and explain what I am trying to do here. So let's write down a definition. Okay, so we are going to start with some function phi n of x. Okay, so let phi n of x n greater than equals 0, of course natural, yes, and phi of x are piecewise continuous. Piecewise continuous in alpha beta. Yeah. Okay, we say the sequence phi n of x, okay, this converges in mean. This is very important, okay, converges in mean. This is the See, there are different kind of convergences. This convergent is convergence in mean to phi of x, to phi of x with respect to the weight function r of x. Okay, the weight function r of x. See, here I am incorporating r of x. If you want, you can just take r of x to be 1. It's not a problem. Okay, in alpha beta, if this is the meaning, see, what we are saying is this: the norm of phi n minus phi, is it okay? That if you take the square of that norm and then you take the limit n tends to infinity, yeah, that is okay. Let me just write down what is the definition. That is given by limit n tends to infinity. What is this norm? This is nothing but the integral alpha to beta r of x phi n of x minus phi of x square dx. Okay, this is going to be 0. Yes, we talked about this sort of norms and all, right? Yeah, if you remember in the first lecture itself we talked about it. Okay, so we are using that norm. Okay, so this norm is defined by integral r phi square. Yeah, okay, so if this goes to 0, then we say that the Fourier series converges to f of x essentially. Okay, so therefore the Fourier series converges in mean to f of x provided limit n tends to infinity, okay, and alpha to beta r of x Sn of x minus, okay, you don't have to put a mod here, it's basically the same, square is there, yeah, minus f of x square dx. This should go to 0. Is it okay? Then we call this converges and the converges in mean. Okay. So now see, is it okay? Now you see, the thing is, we will see a small thing that what happens, okay, if there is a possibility of representing f in terms of a different series. Is it okay? So basically, let f of x, okay, f of x is represented, it is represented by summation n equals to 0 to infinity dn phi n of x, okay, where phi n are not necessarily Fourier series coefficients, okay, Fourier coefficients of fx. Is it okay? You understand what I'm trying to say, right? See, the thing is, it may happen that there is a different representation which is basically not a Fourier representation, and we can write it like this. Okay, so now and we want to see what happens if we do something like this. Okay, so now define, let's see what happens. Another finite sum Tn. What is the sum? It depends on x, of course, and then d0, d1, dn. Okay, just to specify this particular thing, that it depends, the Tn is a finite sum with respect to the coefficients d1, d2, dn, right? And that is given by summation n equals to 0 to infinity dn times phi n of x. Okay, now and let's say we define capital E capital N. Okay, that quantity is nothing but the norm of Tn minus f. Okay, we want to see what is the difference, Tn minus f, the norm. If we calculate it, let's just call that En, and want to calculate what that is. Okay, now you see, since phi n's are orthogonal, this way is given to us, right? Orthogonal. Then what is En square? Let's just calculate what is En square. En square is nothing but summation Ta capital N minus F square. Is it okay? And that is given by definition, what is it? It is alpha to beta R of x, and then summation dn phi n of x, n equals to 0 to infinity, minus f of x square dx. Is it okay? Yes, we can write it like this. Now, you see, we can just break it up. Yes, let's just break it up and write it. So, this is nothing but summation n equals to 0 to infinity, okay, dn square alpha to beta r of x alpha phi n square and dx. The first term, right? What about the last term? Let's just write down the last term now. Plus alpha to beta r of x f square of x dx. The last term, and then the middle term 2ab term minus 2 times summation n equals to 0 to infinity dn integral alpha to beta r of x phi n of x f of x dx. Okay, let me just check once if everything is fine or not. Yeah, this is okay, right? This seems everything is fine. Okay, now you see what exactly is this term. This is nothing but phi n square, right? So this is nothing but summation. I am not writing 0 to infinity. It is always sorry. What am I doing? Sorry. This is not 0 to infinity, right? This is 0 to n. Huh? Sorry, I am doing it with en. Huh? So this is 0 to n. That is why I can change the limit. Sorry. Yeah. This is my mistake. Very sorry about it. 0 to n. Yeah. Okay. So 0 to n I am not writing. Okay. So that is given. Because it is a finite time, I can take the integral inside. So it's not a problem. Yes. Okay. So this is dn square and phi n square, right? That's just this thing definition, minus 2 times summation dn cn norm of phi n square, okay, plus f square. Is it okay? So I will just write down everything in terms of norm. So that is given by, and of course the integral is from 0 to n. Okay, let me just write it 0 to n. Okay, so if this is true, you see I can write this as summation 0 to n. This is nothing but norm of phi n square dn minus cn square. Okay, dn minus cn square minus sum n equals 0 to n phi n square cn square plus norm phi n f square. Yeah, I hope this everything is fine. Huh? Let me just once check. Yes, this is fine. Yes, 2 times this and plus f square. I think it's okay. Yeah. So you see, if we can write it like this, now the thing is this. You can see that the quantity E capital N, when is this least? If dn equals to cn. Okay. So therefore, capital En, this quantity is least. So basically the norm of capital En is least if cn equals to dn for n in equals to 0, 1, 2, right? Yeah, and therefore see, the thing is, what we proved is the following. Let me just write it there. So we proved this theorem. We proved the theorem. Let me just write down the theorem first. So for a given non-negative integer n, so given n in n, okay, the best approximation okay, in mean, very important, in mean, to a function f of x, f, okay, x, by an expression, what sort of expression? 1, by an expression of the form summation dn phi n x, okay, is obtained when the coefficients dn are the Fourier series of f of x. I hope everything is clear here. Yeah? See what we did, this part is this. Fx we wrote it as summation dn phi n. Dn is not necessarily the not necessarily the Fourier coefficient of f of x. Okay, and what we did is this, we calculated En square, which is nothing but the finite sum with respect to those coefficients dn minus f square. Okay, so in the mean they will converge in the mean. Okay, so you see we have to talk about this particular term. Yeah, that is what we are doing here. Now, you see, En square is nothing but summation Tn minus f square, right? Which we can write it like this. And now, you see, this is a positive term. Yeah. So, when is En least? En is least if Dn is equals to Cn essentially. Okay. So, that's what. So, what we proved is this, that basically if you want to write f of x in terms of a Fourier series, looks like this, n equals to 0 to infinity Dn f phi n x, then the best, the best candidate for the coefficients has to be the Fourier coefficients. Is it okay? Right. Now you see, the thing is, let's say that here, let's just call this thing as 2. Huh? Let's just call this thing as 2. Now, into if dn equals to cn, okay, if the Fourier coefficient, they are Fourier coefficients, so n equals to 0, 1, capital N, to obtain, okay, one second, sorry, this I should write it as a finite. We did it for 0 to n, capital N, right? For any capital N we can read. Okay, so into if dn equals to cn, what do we obtain? We obtain that summation Sn minus f square. Okay, this is nothing but norm of f square minus summation n equals to 0 to infinity phi n square Cn square, right? That's what we are going to get. See, this t's will be s in that case, because the coefficient d's will be d is basically ei's. Okay, sorry, d and c are basically same. dn's and cn's are basically same. So this tn is basically sn, right? Okay, now so what is the norm of sn minus f square? So that is nothing but this one and this one, and this is gone because dn equals to cn. Is it okay? That's why that's what I wrote it here. Yeah. Okay, so now therefore what we can say is this norm of Tn minus f square, okay, that is nothing but summation 0 to capital N norm of phi n square dn minus cn square, right? That's what we actually showed, and then s capital N minus f square. We can write it like this. Yes, the last two terms is in terms of Sn minus f, we can write it like this. Okay, now if we do that, see, since this is a positive term, all of these are positive. Okay, so we can say 0 will be dominated by norm of Sn minus f, which is again dominated by norm of Tn minus f, right? This is a positive term, we can throw it away. So Sn minus f square will be dominated by Tn minus f square, and hence this inequality holds. Okay, now you see, therefore, if summation n equals to 0 to infinity, now it is infinity, yes, dn phi n x, if this converges uniformly, not uniformly, in the mean to f of x, okay, then the Fourier series converges, right? Then the Fourier series, because this is with respect to the Fourier series, right? The Fourier series converges in mean to f of x, okay. But then let's just call this thing as 3. But then 1 to 3 implies that limit n tends to infinity, okay, summation 0 to capital N phi n square dn minus cn square, this equals to 0, right? Yes. See, the Fourier series converges to f of x in mean, right? So basically this is 0. Yes. And of course this also is given to be, it converges, so that is 0. So basically we have limit n tends to infinity, this particular term is going to 0. Is it okay? Yeah. And this is, and when is this possible? See, this is a positive term, this is a positive term, I'm taking a finite sum and then I'm taking the limit, I'm telling that is 0. It only happens if dn equals to cn. Therefore the above is only possible, above is possible only if dn equals to cn, okay, for n equals to 0, 1, 2, it goes on like this. Is it okay? Yes. And what we proved now is essentially this thing. So let me write it here. What we proved is this theorem, theorem 2. What is this theorem? So if a series of the form summation 0 to infinity dn phi n of x, okay, converges in mean to f of x. Is it okay? If it converges in mean to f of x, then the coefficients dn must be the Fourier coefficients of f of x. Okay. See, we just saw, right, that if if you have something like this, that dn converges to f of x in mean, then it has to be the Fourier coefficient, dn has to be cn. So basically that's what we showed, that if the series converges to f of x in mean, then it has to be the Fourier coefficient. So the series converges is basically the Fourier series, that's what. Okay, right. So now also let's see, also, yeah, so this is proved. This is proved. Now let's look at a different thing here. See, the thing is, from this inequality, I don't know where I wrote it. Yes, here. Let's just call it star. Also, from star, what do we have? We have 0 is Sn plus 1 minus f is dominated by Sn minus f, right? See, star. So basically if you are taking n plus 1, there is another term. So we are basically have a decreasing sequence, right? Non-increasing sequence, that is. Okay. So thus this sequence norm of Sn minus f, okay, and n equals to 0, 1, this sequence is non-increasing and bounded, okay, is non-increasing and bounded. Okay, below by 0, of course, below by 0. Okay, what does it mean? It means that it must converge, right? And if it converges to 0, then of course the Fourier series fx converges to the Fourier series of f converges to f of x in mean, right? See, of course, right? If Sn minus f, this sequence, that basically converges. If it converges to 0, though, so there basically in that case we just say that the Fourier series converges in mean. That's there. Okay. So also we'll have this. See, summation n equals to 0 to infinity phi n square cn square is dominated by norm of f square. Is it okay? Yeah. That is true. Now, because of this, right? See, because of this is always dominated by this always dominates 0. So basically phi n square minus cn square is dominated by f of f square, right? Okay, now you see the sequence. If I now, since the sequence Cn, what is Cn? Cn will define it to be summation n equals to 0 to capital N, okay, phi n square cn square, okay, this sequence, and n equals to 0, 1, 2, yes, is non-decreasing and bounded, above by bounded above by norm f square, okay, it must converge, clear? Okay, and therefore what we have is summation, one second, I did a mistake again here. It should be up till n, because all of those earlier calculations are up till n. So then it must follow that 0 to infinity norm of phi n square cn square must be dominated by norm f square. Yeah, this is non-decreasing and this holds for all n. So basically I can write it as the up to the sum is from 0 to infinity, right? We can do that. Now you see, therefore what we can say is, therefore the Fourier series okay, of f of x converges in mean to f of x, converges in mean to f of x. Yeah, if and only if this is true, right? If and only if this and this is true, right? So summation f square is equals to summation n equals to 0 to infinity phi n square cn square. Yeah, I hope this is clear. This converges if and only if norm f square has to be equals to this. Yeah, okay. So now this inequality, what we wrote here, this is very important. This inequality is called the Parseval's inequality. So this is called, how do I put it? Maybe I can put it in a red. This inequality is called Parseval's inequality. Is it okay? Yeah, and this particular inequality, you see, if phi n's are basically orthonormal, so let me put it this way, small note. If phi n's are orthonormal, then this thing implies that summation phi n square 0 to infinity is always dominated by f square, okay, and this is called Bessel's inequality. Yeah, I hope this is clear now. Okay, so let us put everything in summary, and I will put it in red, so that it becomes much clearer what we did up till now. Okay, so let me put it as this theorem. So this is about Fourier series. So we start with phi n of x. Okay, phi n of x, and this is for n equals to 0, 1, this thing. Okay, be an orthonormal set. Is it okay? And let Cn be the Fourier coefficient of f of x, given by f of x is summation Cn phi n of x. Is it okay? So this is between n equals to 0 to infinity. Yes. Okay, then the following holds. following holds. Following holds. What is that? So it is A, the series, this series summation 0 to infinity Cn square, okay, converges. This is what we showed, right? You see, it is dominated by norm f square. So basically, this series converges Cn square, okay. And what does it mean? It means that limit n tends to infinity Cn equals to limit n tends to infinity integral alpha to beta r of x phi n of x f of x dx. This is going to be 0. Okay, see, the thing is here that norm of phi n square is not there because phi n is taken to be orthonormal. Okay, right. Now B, the second thing is the Bessel's inequality holds. Bessel's inequality, what we wrote this last page, this inequality holds. Okay, Bessel's inequality holds. And C, what is the C which you have? You have that the Fourier series of f of x okay, converges in mean to f of x. Is it okay? If and only if the Parseval inequality holds. If and only if Parseval's inequality holds. Is it okay? Yes. So this is the idea of Fourier series. So basically what we have is this. Let me conclude what we had did and where is it coming from. See, we know that if you have a regular or a periodic sum level boundary value problem, then basically corresponding to the distinct eigenvalues, we are going to get a series. So basically a infinite series of orthogonal functions, right, which we are basically we call it an eigenfunction. And the thing is since they are orthogonal, okay, that set we can start with and we can actually formulate a Fourier series out of it. Yes, and then we can represent any f with respect to those Fourier series according to whatever theory we just developed. Okay, so that's the idea. So basically what happens is, if you want to produce different Fourier series, where are you going to get the supply of f of x? Those supplies are actually we can get it using the Sturm Liouville boundary value problems. Okay, so with this I am going to end the video.